Okay, guys, I'm sorry about this, but somebody set this projector up so that I cannot get this to just show up as the presentation. This is the best I can get it. It's only putting it on this screen, which I can't put on the projectors. So I'm sorry, but you're gonna have to look at it this way. I can't figure it out. So we're gonna talk about two different things today. First, I'm gonna start talking a little bit about aesthetics, which I've touched on. With your maps, we talked about putting a legend and a scale bar and a north arrow on it, but there's more to it than just putting the information on the map. Your map is only as good as what your viewer can get out of it. So what's wrong with these two maps? Anything, just tell me right off the bat what strikes you as wrong about these.
The legend is hard to see in the map.
Yes, the legend is really hard to read in both cases. In one, because it's written in white over top, and in the other, because it's overlapping the map and it doesn't color very well. I can't even see where the north arrow is on one of these. In this case, it's up here in the corner over here. The scale bar is really hard to read. These are just bad maps. It's a good example of bad maps. So, two more maps looking at essentially the same information here. Well, it is the exact same information between these two maps, but one of them is done right and one of them is done very, very wrong. And in fact, this is going to be your homework, is to correct this map using your reading from the chapter. I think it's chapter 5 in the current textbook. But right off the bat, the first map has really garish colors that are hard to read and hard to understand. The colors don't really correspond well to anything on the legend. You'll notice the legend is just, seems like a random scramble of numbers. They're not, they're capitalized improperly. And all of the towns are displayed with red pluses instead of actually showing anything that makes any sense, like the population by size and whatnot. The second map, the labels are legible because there's a halo on them. You can see them on that dark background. The textbook will tell you that people tend to prefer just visually pastels and earth tones. So this map is done in kind of earth tones, a little easier to look at. The colors correspond to something that you can actually understand the label of, square miles. This color works well with the color scheme, and you can see the roads on there because it's a corresponding color. We've got dots instead of plus signs for the labels. These two maps work, but they're not exactly ideal. Look at the white space you have and how you want to lay out your map. If you're going to put multiple items on a map, figure out where your items work, how to arrange them, etc. And if your background is too heavy, you know how to change the transparency on your background so that things show up a little better. All right. So what's wrong with this one? This is getting into what we're really going to dive into today. I don't have a handout specifically on step-by-step instructions today because I want to introduce a subject that we're going to cover today and next class. We're going to spend some time on. We've done how GIS looks at the files we give it. Now we've got to talk about how the files actually work and what the coordinate systems are and whatnot. So what do you see that's wrong with this map? It's not aesthetic. Something is wrong with this map that just looks odd.
Stretched weird.
Yes, the state of Montana is stretched out all strangely. The video I showed you on the first day talked about how our projections actually make our maps look. In this case, if this is an unprojected map of Montana, it doesn't have a projection on it. It is simply stretched out to fit the entire globe. This is the Mercator Projection, which takes the entire globe and lays it out flat as one big box. And anything closer to the poles gets stretched out really bad. Montana's about halfway to the North Pole, so it gets stretched pretty badly. You can see side by side what Montana actually looks like, the size and shape of Montana in reality on a globe versus what it looks like unprojected. The map on the right is actually Montana projected. So obviously, if we're looking at Montana, that's not the way we want to look at it. If we were looking at the entire globe, sure, that's fine, because we're trying to look at more than just Montana. But if we're looking at an area-specific location, it's really important what projections that you use to present your data. You know from the last two classes, we talked about where that information is stored. It's under the source tab for all of the data. Today, we're going to dive into actually using that and what it means and what it ends up looking like. The important thing for you to remember here is coordinate systems versus projections. Coordinate systems are nothing more than a Cartesian plane that lays everything out on the globe and gives you a precise location for something on an XY coordinate plane. So it's a Cartesian coordinate plane saying at 45/35, this is where this location is. That's your coordinate system. Your projection is how you look at that coordinate system. Do you look at it from space like this and stretch the whole thing out to fit on a two-dimensional surface? Do you look at just a single location and say, that's what I'm looking at, everything else is not interesting and can be warped however you want? How you look at it is your projection. So we're going to open up ArcMap here in just a second. Actually, I should have you download all of today's information from Teams. And go ahead and open up a blank instance of ArcMap. So I'll give you a second to start downloading that stuff from Teams before I go on. Today's folders 2.1. I've got homework in there, but what I want today is this folder GIS data. There's not a lot in there, but we're going to manipulate that data today to look at coordinate systems and projections. Okay, if you've got that downloading, we can keep going. In ArcMap, we have looked at two different folders for these coordinate systems. There's geographic coordinate systems and projected coordinate systems. So everybody's a little bit confusing in how they present this. Projected coordinate systems, think of that as projections. Everything, no matter what, has a coordinate system. Not everything is projected. Your coordinate system is basically latitude and longitude. Where does it exist on a plane? Your projection is how you look at that location. So we have a couple of different types of projections that people typically use. There's the point projection, usually used for the poles. We'll look at the North and South Pole today. There's the conical projection, where you actually take a point and kind of wrap a cone around an object. Let's see. I have my little, for lack of anything else, I have my globe today. If this was the Earth, and we wanted to look at a point, you look at it flat on, and everything you see is kind of like a photograph in the point projection case. So what you see is what you see. In the conical projection, you take a point, kind of create a cone, look at it like this. So you're looking at this point, and everywhere it touches that globe is what ends up printing on your piece of paper, on your two-dimensional surface. Okay? Trying to remember what the third one is. Oh, cylindrical. So similar to the conical, in this case, you just wrap it around in a cylinder, and everywhere it touches that page, that's where you've projected your map onto your piece of paper. So we're trying to take a three-dimensional object and turn it into a two-dimensional piece of paper or page or screen, in this case, and accurately project the area that we're interested in. Whether we're interested in a point, right here, we point a cylinder around that and look at that point. We're interested in a line, where we take a piece of paper and wrap it around it in the cylindrical projection, or we're looking at just a flat surface and only the part we can see is what we're interested in. So what that ends up looking like. We're going to go through and look at a couple of these. If you'll open up blank instance of ArcMap and bring in the world countries file from the GIS data folder. This is a cylindrical projection, one that you're probably comfortable with seeing in the past, called the Mercator Projection, where you're looking at the entire globe as a point and stretching the entire thing out. The only place on this entire map where it's actually accurate is smack dab in the middle, prime meridian and the equator. Where those two places cross is the only place on this entire map that it's actually accurate, in size, in distance, and in shape. Everywhere else it's distorted. Now, if you would, please, we're going to start playing with how we look at these. I would like to show you a cylindrical projection and a planar projection. We're going to use this same file to do that. I'm sorry, this was a cylindrical projection. We're going to look at a planar projection. So instead of changing the data that actually exists in our file, like we did before, we changed the coordinate system in here. We're going to look at the way we view it. We're going to change the way we view it. You have two different things happening here. If you right-click on your file itself and go down to Properties, we'll see that the coordinate system this is in is GCS, which means it's not projected. It's in the GCS WGS 1984 coordinate system. All that means is that the latitude and longitude location of all of these files comes from the Cartesian coordinate system WGS 1984. Now what we'd like to do is actually project it and see how it looks. We're going to do that by changing the way we're looking at it through the data frame. So right click on layers and go into properties. And let's take a look at an orthographic projection, which is a planar projection, and one of the planar projections we commonly use in Montana is state plane. I've mentioned state plane to you, and I might have had you favorite it, but this is a projected coordinate system. So open up projected coordinate system or a projection. So I should probably start saying that. If I want you to think of it that way, I should say that. These are projections, not coordinate systems. These are ways to view coordinate systems. So let's go into state plane, expand that folder. We'll just pick NAD 1983 meters and scroll down until you see Montana. So we're going to focus on the point of Montana and just say, okay. If you get this warning, just say yes. They're warning you that the coordinate system doesn't match what the file is in. And you may have to hit your little globe to completely zoom out. Give that a minute to load. I gave you a handout with two common coordinate systems. There are two coordinate systems really commonly used in the United States. One is a point coordinate system or a plane coordinate system, and the other is a cylindrical coordinate system, I believe. Transverse. So UTM takes a line. UTM says this longitude line is what I want to be accurate. Everything outside of that can be distorted, but this is what I'm interested in. State plane takes a point and says that's what I'm interested in. Everything outside of that can be distorted. Montana is unusual, as you can see from the map, in that we only have one state plane for the entire state of Montana. So it's actually a little bit distorted already just because that's a really large area for a single point. But you can see the UTM zones are divided over Montana into UTM zone 11 north, 12 north, and 13 north. So those three make up the state of Montana, and where you are in Montana determines which UTM zone you use. But you can see, if we look at the world from the perspective of just the point of Montana, it works the way we see it, but what we're interested in is Montana, so that is the only part of this map that's accurate. Looking at it in UTM 12 north, let's go ahead and go back into properties. this time, projections, UTM, and we're going to use a North American NAD83 coordinate system, so expand North American, and we want to use just plain NAD83 2011 UTM zone 12 north, because that's the center of Montana, and say okay. Again, you're going to get this warning saying it's inconsistent. You might have to blow it up again too. But what we've done here is say this line down the middle of the map, this longitude line, is the only part of this map that's accurate. Everything else in this map is completely inaccurate, distorted, misshapen, because the only thing we're interested in is what falls along that line. Okay, so I'm gonna shrink that for now and come back to this map. What that does is how you project your file actually changes the distance and the shape and the area of your files. So you need to be aware of what you're looking at this file in, but you also need to be aware of what your file is actually in. We're going to take a look at this and go through it, but these are the two coordinate systems. The larger the area, the less accurate your projection is. Your coordinate system is an accurate location. Your projection is only as accurate as the area you're looking at, but we're looking at length and shape and what it actually looks like in reality with a projection. And this is what you get when you overlay them. We'll actually do this here in a minute. They're all a little bit different. The unprojected files that are just in a coordinate system, those are accurate only in the fact that they have a numerical location. Everything else about them is inaccurate. The other files, how you view them determines their accuracy. So that's why we have this exact same file displaying in all these different locations. So your coordinate systems accurately locate your things, all of your files. Your projections accurately show what they look like, but they are always just a little bit mislocated. Just a little bit because, well, I guess the larger the scale you go, the more mislocated they are. But keep in mind that your projections are always a little bit incorrect in their location because of the way you're viewing them. So I've said this over and over and over again throughout the class, but you probably didn't know what I was talking about. On-the-fly projection. We're going to do on-the-fly projection today. We're going to look at GIS doing that. What GIS does is it says, you told me my coordinate system is UTM zone 12 north because that's what my data frame is in. Even though my data frame is in UTM zone 12 north, that's what I'm looking at it in. My file is in an unprojected coordinate system, WGS 1984. I'm seeing this in a projected coordinate system, even though my file is not actually in that coordinate system. That's on-the-fly projection. It's letting you see it. Now, what GIS does that is fantastic, but also very tricky, you have to be careful of, you can have 12 different coordinate systems in here, and you're looking at all of them in the way you're viewing your data frame. Every time you bring in a different coordinate system, you bring in a little bit of inaccuracy. If we're just printing out maps of counties, who cares? Nobody's ever going to know. But if we're actually plotting flight, transatlantic flight, based on these little inaccuracies, you can crash a plane. It's really important to keep in mind what you're doing and how accurate it is based on your projections. So I am going to, actually I think there was one more slide. I'm going to introduce today, for the first time, our toolbox. So far, all we've done is look at files and manipulate them a little bit, how we see them, how we display the data that's actually in them, where we store them. Today, we're going to take those files and we're going to manipulate them. We're going to change how they work. This is really the heart and soul of GIS. This is what differentiates GIS or ArcGIS from Google Earth. Google Earth is not an analytical mapping tool, but it's great for displays. It makes beautiful pictures, but it has very, very limited analytical capabilities. This software is an analytical workhorse. You can do anything with it. The trick is to figure out how. So let's dive into actually looking at this today. I'm going to have you open. Please close the one that you had because I don't want to fool with different projections. I'd like you to open 3 different instances of ArcMap that are blank. Don't delete out the files you have in them. Open 3 new instances. All right, one by one, we're going to create the same map in each of these 3. I've got 2 different projected files and 3 different shape files in here that are all the exact same file. I'd like you to add 1 to each map, just 1. And if you bring in, pay attention to which one you bring in. So bring in MTSP, that's state plane, and name your layers after that. Say properties, state plane. So we know what coordinate system we're looking at these in. And on each map, I'd like to do the same thing with a different file. So this one's UTM. All right, what I'm interested in is 2 things: looking at the distortion of lengths and measurements, and looking at how we can measure those. Go ahead and each one of these, bring in towns and put them on the top on each of the 2013 towns on each of the maps. Just put them where you can see them. But what I want you to recognize is the first file you brought into each file defined your coordinate system for your entire data frame. So in this state plane, my coordinate system automatically read and said that this is state plane feet. It recognized the coordinate system from that file and assumed that I wanted to look at everything in this data frame in state plane feet. Same for my other coordinate systems. My UTM data frame is in UTM zone 12 north now, because the first file I brought in was in the coordinate system UTM zone 12 north. And this one is in WGS 84, which is technically unprojected. Although we are looking at it on a 2-dimensional plane, it is technically unprojected because we're not applying a way to see this. We're just rolling it out and looking at it. So we've got these 3 different coordinate systems. What we want to do is take a look at how the measurements differ. Your measure tool right here, if you click on that, it's on your tools toolbar. Click on your measure tool and you'll get this little pop-up menu. Start with your WGS 84 file, so we're all looking at the same one. What I'd like to do is look at how we measure across this state. Does everybody have their little snapping feature on? Because that's going to be nice for this one. Okay, so snapping will automatically jump to the location you're looking at. We have measure a line tool. We have measure an area tool. We have measure a feature. So, well, we're not really going to be able to measure these features because they're little point locations. You can sum up all of these as we go if you turn that on, and then you can decide how you want to measure. If you do this little drop bar, you can measure your distance of your lines in whatever. Set yours to miles. We're going to start with miles. You can clear your results. And these are the different ways that we're actually measuring. Geodesic looks at the world as a globe. It's measuring across the surface of a circle. Loxadrome is a little more complicated. It's not a direct line between these 2 points across the surface of a round surface. They're actually following the closest, the best way to describe this is that it's following the closest straight line that's been defined as a latitude or longitude line. So Loxadrome actually does these little tiny little jagged motions. You're not going to see much of that in the measurement because it is so minuscule, but they kind of do these little jagged down and over instead of going straight across. And great elliptic assumes the planet is not actually a perfect sphere, it's more like an egg. So we have this kind of oval shape instead of a sphere for great elliptic. So how these measurements differ is pretty minute across Montana, but it's enough that you're going to see the difference in a lot of cases. So let's start with this line tool. Pick the town in the top left corner, I don't even know which town it is, and go to the bottom right corner and click on it. If you drop a single point, it's going to drop a single line. It'll keep measuring if you move your pointer around, but what I want you to see is I chose great elliptic. I'm measuring in the great elliptic. My segment between those 2 towns, oh crap, between those 2 towns was 594.92. I'm going to write this down. It's great elliptic. So change your measurement. Oh, it won't let me. Change your measurement to Loxadrome and make that same measurement.
So what if it doesn't let you change? Am I doing something there?
Double click on your map somewhere so that it has lifted that line. That's what happened to me.
There we go.
Yeah, so do that same measurement from whatever town to whatever town. Four, 42047. All right. And same thing, try it with geodesic. If you double click, it'll just drop that point. Geodesic and Loxadrome, or I'm sorry, great elliptic and geodesic came out to the exact same measurement down to however many decimal points that is, because this isn't a big enough area for that egg shape to matter. If we were looking across the whole globe, we would see that. But the Loxadrome, where instead of measuring like this, we're measuring like this across that line, added a little bit of space, it added a little bit of distance. So in this case, Loxadrome is terrific for navigation. If you are trying to go across the Pacific Ocean and you're aiming for that point, it follows a direct line. So you might add some distance going around that shape, but you know exactly where you're pointed the whole time. But it's terrible for measuring on a map. All right, let's go over to, actually, well, let's see. So this is based on the coordinate systems. It doesn't matter which projection you're in, because the projection changes the way you see it, but it doesn't change the actual location. So let's actually stay on this one, on the unprojected WGS. I want to point out here that we can't measure an area. The area measure tool is shaded out here because this is unprojected. It's not displaying right. Therefore, any area measurement will be wrong. So it stops you from measuring an area. Let's go into one of the other two that is projected. We can take a look at measuring an area. If you want to just pick 4 towns, we can do this. Use your select tool and hold down shift and just pick 4 towns. That'll give you something to shoot at for your measurement. That's an unfortunate color scheme for this. Maybe I'll change this background so you can see that. So let's use the measure tool and look at that again, this time using area.
Every time I click on a town, it outlines my whole.
So, because we haven't specified that it only wants to select the towns, it's trying to select the state as well.
Yeah.
That's okay. We're just looking at these right now. So if we take this measurement area, we're set on area here, check and see what units you're in. I'm in miles. We can put this in acres, or I'll put it in kilometers, whatever. Draw, each point puts down a corner. Draw your box, and you can finish it by double clicking. My area is 171,192. And that was measured in planar. Planar is completely different from the others. Planar is assuming that the world is not a sphere. It's a completely flat surface. We're looking at an area as if this was completely flat. It doesn't take into account any of the contours of the globe. You can't change that here. You're going to be measuring in planar in certain coordinate systems, but if you want to change that and try, let's look at a couple of different ones. Oh, I've got the wrong one. This one's not going to let me change. Oh, my UTM doesn't want to let me change, and I selected them in there. So let's go to this one, state plane. It'll let me pick different towns. Measuring in. Nope, it's locking me back into planar. It won't let me measure it. Yep, it's only letting me measure in planar. I don't know which coordinate systems will allow you to change that, but basically the point is be aware of what you're measuring in, especially if you're measuring in a line, because the chances are it's not going to be exactly what you think it is. So be wary, navigation versus actual measurements of distance. So what I'd like you to do next is take a look at, we're going to take these and actually start adding information into the different data frames here and look at how these overlap. So I'm going to remove my towns, but I'm going to keep my state plane here. And this is something I haven't shown you guys. This is kind of cool. You can shrink all of these different tabs. So you have multiple maps overlaying here. You can, oh, don't do that on me. You can actually drag from one map to another. So I want to put all three of these on one map. You're probably going to get the warning that they're cross coordinate systems. That's fine. So take each one of these, you can close your measurement tool, take each one of these and change the color of the outline. I want to blow it up and change the color, but make it hollow so I can see just the outline. I'm going to make one red, one blue, and one black. All right, I happen to do this in my state plane map. Doesn't matter which one you're working in. Whichever one you brought it into, your map should look something like this. Opening these one by one, my properties of the black file is in state plane feet, so it's in a point coordinate system. My properties on the red file says that my UTM is in NAD 8312 north. My blue file says I'm in WGS 1984, but I'm seeing them all in exactly the same location. If you drag them around, you can see that the reason we're not seeing all three at once is because they're overlapping. I'm seeing them all in my data frame in state plane. Okay, what I want to do is look at these individually and see how they're different. We're going to start adding more data frames to our map. What I'd like you to do now is insert a new data frame. Okay, and do that again. Insert 2 new data frames. Now go into layout mode. We've got 3 different data frames. I'm going to put this in layout mode so we can see the entire state. That's File, Page and Print Setup. Go to Landscape. And I want to take this box and spread it to fit my page. That's my first data frame. That's state plane. I know that one is the one that I was dragging and working with because that's the one that's in bold. If I go back to my data view, I'm looking at this one because it's in bold. If I activate my second data frame, it's going to be blank. There's nothing in it right now, but I can do that so that I'm looking at that in data mode, right click, activate. That one's blank. I want to actually populate that one. Well, we'll do that in a second. Let's go back to layout mode first. Grab your other data frames and drag them to match exactly the data frame you brought to meet your page. I want them to perfectly overlap. And just to fill the screen, zoom to layer on one of these 3 so that we've got Montana filling our screen. Now I'd like you to go back into data view and pick one of your inactive data frames. Populate the other 2 data frames and remove so that you've got one of these in each data frame, and remove the other ones so that these are split into 3 different data frames. We have a state plane data frame, we have a WGS data frame, a state plane data frame, and a UTM data frame. And they should be hollow with 3 different colors.
I'm sorry, how did you get that data, the new data frame?
Insert
Insert, okay.
data frame. Now, if you don't have 3 data frames, make sure you go into layout mode and make all 3 of those data frames exactly the same size. I goofed this. See how my data frame says state plane? I left WGS in that one. So I'm going to change that data frame to WGS 1984. If you did that, if the file you left in your first data frame does not match the name of your data frame, change it to match your data frame. Properties on the data frame. My case is WGS 84. That one's GCS, World, WGS 1984. If yours was state plane, it's projected coordinate system, state plane, NAD 1983 international feet, and then pick Montana. So I'm going to change that name. Sorry about that, I wasn't paying attention. But now, because I brought my state plane first into this data frame, it should be in state plane. And same with the third data frame, I brought in my UTM file first, so my data frame should be in Universal Transverse Mercator 12 North. Now I'd like to go back to layout view. And on each of these three, right-click on the Montana shapefile and say zoom to layer on each one. This is what it should look like for you, or something approximate. Is everybody with me here? Because if you're not, I'm gonna send Tyler around to get you caught up. You okay, Ashley? You're good? Okay, so what we've got here is an unprojected, in my case, blue state of Montana, and two projected Montanas that are just a little bit off of one another. In my case, the red one is the UTM Zone 12 North. That's the one that follows a latitude or a longitude line. So what it's saying is, through the center of Montana, we are accurately locating this. State plane in black on my map is saying the entire state of Montana is accurate over this large area, but it's slightly different from UTM because it's a different type of viewing. Those are both as accurate as they're going to get, but you can see they're just a little bit mislocated. So my blue file has the correct location by number, but doesn't look right. These two look right, but are just a little bit off location. My measurements for these two should both be very accurate and very, very similar to one another. If we were looking at the entire globe, we'd see it a little differently. But this one is not going to measure anything accurately. It won't let you measure area, and it looks all warped. Okay, does this make sense so far? All right. So we're going to open up Arc Catalog, and I'm going to show you how I created these three files from one file. These are all the exact same shapefile, believe it or not. All I did was change the projection. Now that is not the same as going in here and saying properties, XY coordinate system, and changing it. If I do that, it doesn't know that the location has changed. So we have to actually tell it, this is in the right place, but I want you to put it in a different coordinate system, so you have to do a mathematical correction to keep it in the right coordinate system in a different projection. So what we're going to do, open Arc Catalog, this little red, or I'm sorry, Arc Toolbox, this little red box up here. Why in God's name is that crashing? Okay, Arc Toolbox is just like Arc Catalog. You can drag it around and hover it. I like to keep it as a tab on the left side of my screen, or on the right side of my screen, where I can pop it open. What I want to do is project one of these files. I'm going to take Arc Catalog, find Data Management Tools, and expand that little toolbox. Scroll down to Projections and Transformations and expand that one. And what I want to do is project. I want to project my file. I'm not saying the coordinate system is wrong, change the coordinate system, which is what I would do if I was doing this through Arc Catalog. In that case, I'm defining the coordinate system, or defining the projection, okay? This is going to be really key, the difference between project and define project. In that case, I'm defining the projection because it has a location. I'm telling it it's in the wrong coordinate system. In this case, I'm telling it it's in the right place, and it has an accurate coordinate system. What I want to do is have it calculate a new one. So I'm going to input, we'll do Montana State Plane because that's the one I have active. And I'm going to project that into a different coordinate system. So I'm going to pick a location. Instead of my default geodatabase, I'll put it on in my GIS data folder. And we'll call this one Project WGS84. Because I'm going to project this into WGS 1984. The next step is to pick what coordinate system you want to put it in. Open that up and say WGS 1984. That's geographic coordinate systems. Scroll down, world, expand that folder, scroll down, near the bottom, WGS 1984. Okay.
So when we did our first input, we're doing Montana State Plane.
Sure. Just, it doesn't matter which one you want to start with, just pick one that's not WGS 84, because then you're just projecting into WGS 84 from WGS 84. We're not going to get into geographic transformations. Ignore that. But I do want to show you, you're going to have this on every single ARC toolbox we open. This little show help menu here. If you click that button, it's going to give you some information about this tool. And the cool thing about it is each item you click on has a different explanation. So if you don't know what the output coordinate system it is, it'll explain it to you. If you have this little menu open, it automatically reads what the coordinate system was in that when you put it in. So I said the file I'm reading is state plane, and it reads that coordinate system, says we're going from state plane to WGS 1984. Say okay. You might get, I'm hoping mine will pop up, you might get a little blue projecting with dot, 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 projecting dot, dot, dot across the bottom. It kind of scrolls across. Oh, no, mine didn't do it. Sometimes on the larger tools, it'll do that. When it's done, it'll either pop up with this little blue box with the green check mark saying, yay, you projected properly, or a red X. It'll say there was a problem and that file didn't work at all, or a yellow exclamation mark in the, or a, I guess it's a black exclamation mark in a yellow triangle. That means there was some sort of error, and be really wary of that file. It'll say it did it, but there's something wrong with it. You can actually click on that to see what it did. If there's an error in it, it'll tell you here. You can just click on that. We'll talk about that later, but you can pull up your results menu and look at anything that you do along the way. So I created Project WGS 84. I'm going to drag that into my map. I'm going to activate my WGS 84 data frame and just look at that in data view. So I have the original WGS 84 and I have the new WGS 84. If you open up, sorry.
I'm just so totally screwed up and then I'm trying to fix things.
How did she present?
So what happened?
So and I totally did
Things all ended up in different positions when I tried to put them in. When I
counting.
put in
That's
the
okay.
data frames, and then
I don't know.
I would try to slip the data frames in the same cell position, and then I ended up
So let's see. Wait,
I don't know if it's worth it. I think it's worth it. Saved it.
Oh, right. Oh,
looks like they're all in WGS 84. Yep, all of your data frames are in WGS 84. So probably add in a file in there. But let's we can fix it. So on this data frame, let's go
So you're just going down and
project.
Yep.
Yep.
Well, north?
Yes, we want to go to North America.
Yeah, North America.
Yep.
so these
And then do where down.
services because it is.
Pilot stuff.
Here.
So we want that to go to the screen. That's all.
Oh,
So state file. Yep, it's in the project.
the little icon is
So now you're back where we were. Now what we want to do is
We were
we've got
probably
that
just.
frame active. So we want to actually do that. Let's go up and open the little red icon at the top.
Oh, I don't think I chose anything,
I saved it right here.
but it still came up. Is that weird?
I don't know.
So you can click on that and you can mark it, or also have it at the bottom of your catalog if you ever want to use it that way. Or looking for data management and projections and transformations.
Missoula or Roots? I don't know.
Now, if it's in your action, let me show you. In our toolbox, fun little trick. If your file is actually in your map, when you go to use, oh, I lost my ARC toolbox. If your file is actually in your map, so I have WGS 1984 as my active data frame, so my toolbox is going to assume I'm working in this data frame. Anything that's in that map will be in this drop menu. You don't have to go searching for it through your folders, unless you're looking for something that is not in that specific data frame. So in this case, that data frame's active. I only have WGS84 and project WGS84. Those are the only two files that show up. If I wanted Montana State Plain, I would have to go hunt for it. But you have those two different ways to grab the file, the input file. So we need to give it a output coordinate system, and we also probably don't want to put it in your default geodatabase, so if you have a location. Location is 6A. So when you double click on it, it takes you into the folder. If you just click on it, it's going to say that's the folder. So it's different between picking a location versus picking a.
No, not. That would throw it out. Okay.
Hope you're good with that.
What are you doing? Okay.
Oh, because it's in folder connection. Go into. Yeah, now you should be able to see it. Okay.
Okay, which is where I had,
Yeah.
but then it doesn't show me anything.
Okay, so you're not looking for anything yet, because you got to do one more thing. It looks for that output coordinate system you want to do WGS. Or like, in your case, let's just take Plain, because you get WGS in the actual numbers. So now you can say, okay. Sometimes it shows up, sometimes it doesn't. Your screen pops up, it'll tell you that you have a new one. Okay, when you're doing this and adding your tools, going through this, it's telling you here by these little green circles what you have to do to run this tool. You have to give it an input file. It automatically reads the input coordinate system from that file, so I don't have to fill that out. It's not telling me I have to locate it because it's automatically putting it in my default geodatabase. I don't have a clue where that is. So I don't want it there. I'm going to pick a location. And I have to give it an output coordinate system. Those are the things that I absolutely have to do to run this tool. If I do something funny that it doesn't like, oh, it's gonna let me put a space in it. Apparently this is not one of the tools that it doesn't like spaces in, but very commonly, if you try to run a tool and you put a space in the name, you're gonna get a little red exclamation mark right here. If you click on that little red exclamation mark, it's gonna give you a pop-up menu and says, the name has a space in it. It doesn't like spaces for whatever reason. Some of the tools are fine with it, some of the tools are not. But it's going to be upset about that. So I'm not going to run that again, but everybody's on the same page. We've created 2 different files. I'm going to take that same state plane and I am going to define the projection on this file. This is not the same thing as projecting it. This is the exact same thing as going in, right-clicking on that file, saying properties, change the coordinate system. So this time I'm going to do it through our catalog. I'm going to define the projection. There's not as much information here because it's not doing a mathematical transformation. It's not saying this file is accurately located, change the mathematics of where it is, and put it in this other projection. In this case, it's saying it's got the mathematics right. We just have the coordinate system wrong. So watch what happens with this one. I'm going to use my project, well, actually, oh, here you go, you got a little exclamation mark. So click on that, it'll tell you what it is. In this case, because I already have a projection on this, it's warning me. It's not stopping me from doing it. It's giving me a warning. You already have a projection. If I had a file that didn't have a projection, was undefined, which we looked at last class, then it wouldn't give me this warning. So we'll look at that in a moment. Just ignore that warning, that's fine. I'm going to change that coordinate system to something else. I'm using my project WGS84. Actually, I'm going to change it I'm going to use one of the other ones. I don't want to use the one that I projected because that one I know is correct. So I'm going to take my original WGS84 file and put it in state plane. So I'm saying the Cartesian coordinates are correct. The Cartesian coordinates are incorrect. Put it in this different coordinate system. Say okay. Here we go. Here's a little blue underline that didn't last long. I have changed the coordinates. I've changed the projection of the coordinates in this file. Now, if I refresh my view, these two are not in the same place anymore. They look completely different. I just screwed up my file because my WGS was correct and I changed it. This is the difference between define, project, and project. If your file, write this down, please, please, please. This is really hard for everybody. If your file is correctly located, do not change the coordinate system through define, project, or through Art Catalog. This is really big because this is easy to screw up. I promise you, I'm not just being a snot about this. This is so hard for everybody to pick up. The location is correct. It's in the right coordinate system. You don't change the coordinate system. You want to change the projection by projecting it, not defining the projection. Does that make sense? You guys understand why? What I'm doing, this is my XY plane. This is my coordinate system. I say this is right here. I'm saying this is, we'll say 1, 3. That's my XY location. What I'm doing when I define the projection is I'm saying 1, 3 is correct for XY, but this coordinate system, this layout here is wrong. This is the 1, 3 it's supposed to be on. So maybe 1, 3 is over here and I've made that jump to the wrong location. If it's in the right location, it's actually 1, 3 in this coordinate system. What I'm doing when I project it is saying, that's right. Tell me what that is in this coordinate system. So maybe in this coordinate system, it's 5, 12. So it changes the numbers when I define the projection, and it actually changes it changes the numbers when I project it. It changes the location when I define it. So whether or not it's actually accurately located depends on which of those tools you use. Your rasters. We have project raster. We do not have define projection. When you're working with rasters, just go through our catalog, go in there, properties, and change your XY coordinate system on the raster. Okay, I think this is kind of all I wanted to go over today. If you want to play with it, we can play with it and look at them in different coordinate systems, but our next class is actually going to be a fairly intense one, going through this on a global scale. We're going to look at measurements. We're going to look at how latitude and longitude changes. Oh, and there's one more thing I want to show you. I'm hovering all over the screen. I want you guys to look at these numbers down here as I move around the screen. These numbers right here. As I move around the screen, those change. That's my location, the location of my pointer in the coordinate system of the data frame. Feet doesn't make a whole lot of sense to you. We can put that in latitude, longitude, decimal degrees. Let's talk about that next time, but we can actually see where we're located in the coordinate system by moving this around, and we'll talk about how to change this, but I think that might be a little much for today. Yeah, I think that's probably where I want to quit today, so we're going to get out a little early, but are there any questions about this? This is the underpinning of everything you do. Being aware of what coordinate system you're in and making sure that you understand why you're in that coordinate system and you're displaying it correctly. So if this is unclear, hopefully the next class will elucidate that a little bit, but if you're unclear on this, we got to talk about it, because this is not just looking at your attribute table or your data in a different way. This is how your file exists. Okay? Everybody comfortable? You want to go home early? I do.
When is that homework due that you posted?
1 week. I'll give you 1 week on every homework assignment unless otherwise stated, because I think this one's not a difficult one. What you need to know about this one is that I gave you the map. All you have to do is open it up, link those files to the files in the GIS files for homework, and correct the map. No, that's okay, you're fine. As long as you know.
So mine did do a weird thing. Like I thought when I was, I totally just shut down. I'm sorry. I shut down my.
That's fine.
But when I had my county, you know, I did a county instead. So I said a county. And instead of moving the county, when I changed it to the NAD, you know what I mean? It moved my state. So I wonder, I think I did it backwards on accident somehow.
Yeah.
And I know it moved my state because I had towns brought in too. So it moved my state instead of my county.
You either clicked on the wrong thing to project it, or it's hard to guess without actually looking at it.
I just shut down, and then I was like, maybe I should say something that it would move that, and I thought it wouldn't.
I think after the next class, if it's not clear, because the next class this is like intro. Here, look at this is easy. We'll just kind of look at the underpinnings. Next class is like, okay, this is why and how it actually morphs and changes. So if it's not clear after the next class, we should talk about it.
Okay. See, I understand like doing like different coordinate systems and Z planes and stuff like that, but I don't.
Yeah, we didn't even talk about the third dimension with this.
Yeah,
this right here is every year I teach this class. This is the hardest subject.
Yeah.
In the entire
I'm
class.
sure it is though.
It's not easy to pick up. So if you're struggling with it, definitely we should talk about it. I try a new way to teach it every year. I can't get this one across very well. It's just a difficult concept.
Everyone's so quiet too.
Yeah, you guys don't talk much.
Oh.
I'm learning everybody's names, so I'm gonna start calling you out.
I am the annoying one. It's okay. At least I know that.
But you're not annoying. Ashley, I had a student, I'm not gonna name her because she works here, but she, every 3 steps, she'd raise her hand and make me talk through it. And these classes drug out and out and out, and I thought the whole class was just miserably bored. I swear I thought the whole class was just in agony watching me deal with her. At the end of the semester, 3 students told me, thank God she was in this class because I could not keep up. She was the only one getting me to slow down enough that everybody could keep up.
I know someone that.
So
works
you're
with you.
not the annoying one. What's that?
I know Frankie works with you. And she took this.
He doesn't
class.
work in the, oh yeah, Frankie,
Yeah, that's who I was thinking of.
No,
Maybe Frankie, but she's so quiet.
No, this was
She
back
would
in
like look
2015.
at me to say something.
Yeah, this is back in 2015, and Frankie picked this up really quick.
Yeah.
That's why
We have wine together on Fridays.
Do you?
Yeah.
I like Frankie. She's
Right,
awesome.
She's a sweetie.
She really is. She picked this stuff up really well.
Oh, she's brilliant. I'm like,
She
thank God
definitely
she's one of my friends because I kind of use her to my advantage sometimes,
It's good to have friends like that.
right? So I'll see you soon.
You doing okay, Tyler?
Yeah, I just wanted to get a little help.
Okay, let me stop.
We did go real